Good afternoon. Welcome to week 3 of basic soil science. Uh, I would say good morning. I meant to get this up earlier, but I believe it's probably good afternoon. No, that's okay. I want to talk about this is coming from the soils needs the NCCER NESR soils modules as a lot of the stuff for these first few weeks has come from. We're in section 2. If you want to follow along in your book, hopefully you have received your hard copy. Section 2 is about excavating soils, and that brings us to the swell and shrink factors. If you have completed one of our certificate programs, chances are you have been taught this module or you have been exposed to it. But we're going to go a little bit deeper than perhaps you went and bring out some of this stuff and make sure we're understanding this. This is extremely important stuff in construction. Uh, we deal in dirt, we deal in soils. Uh, we are more about foundations, subgrade than we are two befores and beams, things like that. So let's get started. The first thing that has really good objectives and suggests you take a hard look at them. We'll be going through some of these things. Describe the factors that affect soil excavation, and there are many. Explain what the swell factor is and how to calculate the swell factor of soils. Also, it talks about the shrink factor and how to calculate that. Well, we'll get to that in just a moment. There's some performance tasks in here, which of course we're not going to do. Uh, we don't have results from a field density test and explain what additional compaction effort is needed. We'll get into that a little bit. We'll go through it. Have it in mind for our in-person lab for this course to get someone out and do a field density either with a nuclear density device or a sand cone device, or maybe just dig a hole in the ground and look at the soil horizon or strata as some refer to it. So we will compute shrinkage and compute shrinking and relative compaction for two different types of soil. That might be something we can get done while we're either in Georgia or Oklahoma City, wherever your 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 representative campus is. Banked yards is undisturbed dirt. That's dirt in situ is the Latin term for undisturbed dirt, virgin soil, some may call it, but it never has been disturbed. Consolidation is to become firm by compacting the particles so that they will be close together. Settlement, uh, shrinkage is decrease in volume when the soil is compacted. Keep in mind what we're going to be dealing with here and end up with a scenario that I want you to uh, solve, figure out, or whatever you do with scenarios, is we'll be digging up soil, computing the swell factor, which once you dig a hole, you can't get all the dirt back into it, and it's because of the voids that are formed when it's disturbed and piled on the side of the ditch. We'll be looking at that. Starting up here at the top with the swell factor, it talks about table 6. Uh, and table 6 has loose weight of the soil is less than the bank weight, and that's because it's got voids in it. We'll go down and take a look at table 6. I don't think it's too far away. There. As you can see, loose weight of all of these different types of soil is in pounds per cubic yard is less than the undisturbed weight of the soil, the bank weight. Now, back up the hill here, to the swell factor is the swell factor of soil is found by dividing its banked weight by its loose weight. For instance, if you're given a bank weight of 3,500 pounds and a loose weight of 2,800 pounds, uh, you would divide 3,500 by 2,800. That would give you 1.25. Is that what they're doing? Yes, right here. That would give you 1.25. If you follow us in your book, we're under section 2.1.0, second paragraph. Uh, so, the thing is, the reason we need to know this is suppose we are digging a trench and we're going to put something back in that trench, such as concrete. And so the dirt will be left outside on top of the ground in a pile. It will, in volume, have increased because we have disturbed it. We have dug it out of its bank state and piled it on this in the spoil pile on the side of the trench, and it has become bigger, or the volume has increased because of the air void uh, that evolved after we dug it out of the hole. Uh, the other thing we will talk about will be the shrink factor, and it's going to be down here somewhere. Let's see what figure set now. Figure 17. The thing about there's three figures, 16, 17, and 18. Quite frankly, they have always confused me. I stay with the math on this thing to show me these blocks, and then you add in a little bit here and you lose it a little bit there. And for some reason, in a visual form, doesn't click for me in this case. Most of the time, I prefer visual representation of a problem. But now, for some reason, I've never liked this representation. So I'm going to let you decide. Figure 17 is on down here. And as you can see, they're adding and taking away things. But it just never seemed to be something, it was more confusing than helpful. So I'm going to talk about it in the way that I use it. So instead of referring to figure 17, let's just move on a little bit. Here's material has a bank weight of 1,000 per cubic yard and a loose weight of 800 per cubic yard. So if you divide 1,000 by 800, you're going to get 1.25 again. They're using some figures that are easy. Sometimes you get some disturbing answers, and with using this chart here. But have no fear, the answer you come up with is where you start. But I'm going to give you a little hint. If you are a contractor and you go to a new site, ask somebody. Call the county extension agent and say, what's the swell factor of most of this dirt around here? These guys that know. Uh, that's always a good source. But let's see what we need to do next. I don't want to get in that. The scenario is the big deal. You, for the most part, can probably figure all these things out. Here's the original problem again: 3,500 pounds in the bank cubic yard and 2,800 pounds in loose cubic yard. So after the first loose cubic yard is made, there's 700 pounds of the materials left over. Those 700 pounds are enough to make a quarter of a cubic yard. So that's where the 1.25 comes in. If you want to increase something by a percentage, like we will get into that next week, rolling resistance, where we're adding 20% to an existing payload, you would multiply that existing payload by 1.2. That would be adding 20%, and that would tell you what your load really feels like. in that case. I'm getting a little ahead when I talk about week 4 is a little more intense. But looking at these examples, they kind of make sense. You take wet clay and look at its weight. Loose, it's 1660, but quite heavy when it's in bank state. And look at rock. Look at that. Uh, 75% rock in its bank state weighs 4,700 pounds. But in each case, you would take this divided by, if you're using non-metric, this, and that would give you the, excuse me, that would give you the swell factor. Let me do that. That's 4,700 divided by the loose weight, 3,300. You would have a 1.42 or 1.4 swell factor. So you would expect to get out of, say, 100 cubic yard hole. Once the dirt was on the ground, you could expect to have 100 bank yards times 1.42. You could expect to have 142 cubic yards of loose material. So what does that have to do uh, with what we do? Well, if we dug out, let's say we had a 1,000,000 yard uh, excavation, which, by the way, for big roadways and things, having 1,000,000 cubic yards to deal with is not out of the question. But what if you forgot, after you excavated 1,000,000 cubic yards, what if you forgot about the swell factor when it come time to haul all that material off? You would go bankrupt, because if you took 1,000,000, how many is that? 1, 2, 3, 4, 5, and you multiplied it times a, wait, I need one more, a swell factor times 1.25 equals 125 million. So you got 25 million more cubic yards to haul off. And if it was costing you $70 a load, you would be shutting her down, because that would be quite a mistake. So there's very practical reasons for understanding shrink and swell. This goes on and talks about, uh, well, it goes right to the shrink factor here. Uh, this is talking about loose fill. I'm getting ahead, sorry. Let's talk about the shrink factor. The swell factor, just stick with the math, is the bank weight, or, by the way, the bank volume. Bank volume is a hole that's not there yet. It's what you're going to dig out. So the bank volume divided by the, I lost what I said, loose volume, is going to give you a swell factor for that particular job. But let's talk about shrink factor. Fill is brought into the job site to bring the existing ground to the desired grade. In other words, if you've dug out a big square hole and you're going to fill it full of good soil, it's going to be compacted in the fill. And it goes on to talk about different types of fill, but it ends up saying, fortunately, the method for calculating shrinkage is the same regardless of how the fill is obtained. And I'm not sure what that means, since they went through all this trouble. But this would be bank, this would be loose fill, this would be loose, could be banked fill. Back to the formula. Let's see, where is that? Right quick over here on this other page, these are kind of notes that I wanted to put up here that I consider important. Uh, to avoid settlement, here it is. Uh, let's read this. Fill is brought onto the job site to bring the existing ground, which is fill up the hole, to the desired grade or the roadbed. When a fill site compacts naturally over time due to rain, freeze, thaw cycles, traffic, or weight of the building, it is called settlement. That's not an intentional effort to compact. That's a natural element to compact. That is, the soil particles rearrange themselves over time. And that's not desirable because the ground movement can damage foundations. So you build a house over something that's not well compacted, you're going to get a crack in the slab, perhaps. To avoid settlement, the soil is at the construction site is uniformly compacted before building. You know, remember what it said early on in the section one, that compaction is the intentional action to bring the soil particles closer together. So by doing that, when soil is compacted, its volume shrinks. The amount of shrinking depends on the characteristics of the soil's moisture content, and the degree of compaction, the effort put into the compaction. The shrink factor, the shrink factor can be calculated by dividing the compacted volume, how much is in the hole after you've compacted it, by the fill volume, how many loose yards you brought in to be compacted. And then it says the tricky part is to determine the fill volume. Fill volume can be divided into the following categories. Then it goes around and says, fortunately, the method for calculating shrink is the same regardless of how the fill is obtained. The formula is compacted volume divided by loose volume. I have it over here. Excuse me. The shrink factor can be calculated by dividing the compacted volume by the fill volume. Excuse me again. Have to get some water. Sorry for that little delay. Where am I? Where was that? The shrink factor, as I have noted in my notes, can be calculated, divided the compacted volume by the fill volume. Now let's go back to the book. Uh, right here, for example, when, let's look at this right here. Let's just look at that. For example, when 100 cubic yards of fill is compacted to 80, if you know it's going to be compacted to 80 cubic yards, then the shrink factor is 0.8. In other words, 80, and that's the compacted yards, divided by the loose yards, 100, equals 0.8. And that takes you back to the illustration that I don't like, the cubes. And we're going to stay away from there. I'll leave it to you. If you think that's helpful, you can go back there. So the same formula works for weight. In other words, we talked about cubic yards here, but the same formula works for weight. Here's the loose weight up here, and here is the bank weight. So you could take the bank weight and divide it by the loose weight. The loose weight is filled. So if there are 2,800 pounds in a cubic yard of loose fill, it takes 3,500 pounds of loose fill to make 1 cubic yard of compacted fill. The shrink factor is still 0.8 because 2,800 divided by 3,500, that's we're going to weight now, equals 0.8. And then there's that then we're sticking with this 1.25 factor, and remember that 1.5 is a fill factor, swell factor. And honestly, on most of these things, you can use that swell factor. Uh, and the bank state after compacted. I may confuse you by doing that, so let me stick with the book. Now, how is the shrink factor used to determine how much fill is needed? When a material has a shrink factor of 0.8, then the compacted cubic yards equals 1.25 or 1 1/4 loose cubic yards. The amount of fill can be calculated by dividing once again, the compacted volume by the shrink factor. 1 divided by 0.08 equals 1.25. If an area needs to be filled with the volume of 10 cubic yards using fill that has a shrink factor of 0.8, 12.5 cubic yards of fill will be needed because 10 divided by 0.8 is 12.5. These numbers should sound familiar since they were used previously in the swell factor, and that's what I just said. Using shrink and swell factors, and this is the essence of this section, I feel like, and I'm not going to go and bore you with things that are obvious, but uh, applying the shrink and swell factors. That's what this is, section 230 is all about. Overloading equipment can make it hard to control. Uh, these are reasons why you need to compute it. I'm not going to read what you're sitting there reading. These are the illustrations, and by the way, just because I don't like them doesn't mean they won't be helpful to you. So here we have the scenario, and this is the essence, as I said, of the module to me. The swell and the shrink factors are just to get us to be able to do this. And let's look at this scenario, and this is going to be your problem. I want your assignment. I want you to read this scenario. I want you to the best of your ability, to understand this is pretty simple, just not going to take up your time with it. But roughly, if you look over here in this scenario, and what it's going to tell you is first determine how much fill is needed. If the compacted volume is 100 cubic yards, divide the needed compacted volume by the shrink factor of 0.8. And then you will know you need 125 cubic yards of loose fill. The second thing is to calculate the swell factor. You're going to need it later. The excavated, the bank weight is 3,200 per cubic yard, and the loose weight is 2,850. And you divide that, and here you go. Here's your swell your swell factor is 1.12. And the third thing is you need 125 cubic yards, as it shows right here. And so is this the swell factor 3,200? I'm sorry, is 1.12. So third, you need 125 yards of fill, but how many bank yards do you need? I forgot the word many. Bank yards do you need to excavate 125 yards? Here is the next little formula. To determine how many bank yards you will need, why is that getting in the way? To determine how many bank yards you will need, divide the desired amount of fill by the swell factor. You're kind of turning things around. Here's your desired amount of fill. Here's your swell factor. Where did it go? Right here. Divide the amount you need by the swell factor. That gives you how many yards you need to excavate from somewhere to bring it back to put in the empty hole and compact it. So that means you need, equals 111.6 cubic yards to excavate 125 of fill. Because when you excavate this amount, when you have to excavate this amount, I'm sorry, I'm getting confused. You have to excavate this amount to get the number of cubic yards after compaction. Now then, since there is more to this scenario, and if I haven't confused you, you shouldn't have, this is a little tricky, but this whole thing over here is what I'm really interested in you doing. This will be your assignment. I will put it, uh, I'm assigning it to you now, but I'll remind you in the assignment. You will do the 3 steps. You will make sure you know the scenario, the 3 steps we just went over. If I confused you, you can unconfuse you. You can call me and ask me a question if you like. But what we're going to do over here is pick out the right truck for the job. If I quit clicking that. This continues on the second thing and the third thing that I briefly went over here. Now, you can verify this calculation in this paragraph here if you would like. Here is the problem. Here's your real assignment. Select the truck that best suits the needs of this excavation based on weight and volume. Table 7 shows the volume right here. Where'd it go? Right here. This table, I can't see both. Select a truck. Table 7 shows the volume and weight capacity for 3 articulated trucks. My instinct was telling me to select the truck with the largest payload so you can get your work done quickly. This is a good instinct, but you need to check that the weight capacity is acceptable for the material you're hauling. To haul, because the cost of operating a large truck is greater than a small one. But let's go back up here. Look at this table. So this is what you're given. You're given a truck model, truck A, B, and C. You're given the volume that this truck will hold. This one will hold 30 cubic yards. This one's 22, and this one is at 19. So you have the volume capacity heat. In other words, that's just piling it in there, assuming that it will fall into the bed of the truck at the angle of repose, which is 2 to 1. That'll be the slope on each side of the pile once it's thrown in that truck. If you've ever seen soil dumped into a truck, you know it falls in there in a conical shape. So it's not taking advantage of this full volume. Now, a struck cubic yard here is filled to the brim. In other words, it's level all the way across the truck. And as you can see, this is the rated payload of 52,000 is the rated payload for truck A. This is the rated payload for truck B. And look at this one, can carry 84,000. So what you're going to have to do is look at the cubic yards of, let's see, truck weight is 22.8 multiplied by 2850. So I guess I can go through this. It's just telling you that if you have 2850, if you go back to the excavation weight of the soil, let's read it to make sure. So truck A, the struck weight is this. All of the available truck can carry the load when struck. To get the job done as quickly as possible, you would select the largest truck. That's the enter, I think. Divide the total quantity that you need, 125 yards, by the struck volume. Uh, if I confused you, I'm sorry, but you will figure this out. It tells you all you need to know is you're using this as the weight per cubic yard. So remember, you will be using this volume. Multiply the volume times this, multiply the volume times this weight. Make sure you don't exceed this. Make sure you're not getting too small of a truck, and make sure you're not getting too large of a truck. What you want to find out, I'm not going to tell you that, the book may, but you need to figure out how many trips it's going to take you to haul that much weight. And with that, I will leave you with, you can go over this or do what you will. I do want to add that we're in the third week. At the end of the third week, of course, we'll be entering the fourth week, which has to do with a little bit more complicated things. And I want to remind you that I first started out with a synchronous class. If you feel like we need a synchronous class instead of these videos, you just let me know. I don't care if it's just one of you. I'm happy to give it. It just seems like I had a hard time getting people to attend, and it's not like it's not worth it, but it is worth it, and I'm willing to do it. You guys might want to get together or in a discussion. Maybe I'll set up a discussion and figure out a good time for uh, face-to-face classes. Things are going to become increasingly more difficult as we move along. Week 4, that's coming up, will be our last week in this NCCER book, and then we'll go into our ebook. And if you've been in there, looked around, you can see that even the language is a little bit complicated. But we're not going to work on the calculations as much. We will do some, uh, and if they're difficult, you're not going to be graded on them. I just want you to experience them. So let me know one way or the other if you think we need to have it, these synchronous, these face-to-face blue button classes. I may set up one or two anyway, even if I'm uncomfortable with it. And with that said, good luck. Be sure and let me know if you're having problems, and we'll talk to you later.